Now we did the regular trig functions. Now we're going to do double and half angles. Those are continuations that we did last time. For example, if we had cosine x plus y, what was our formula for that? Those are sum and difference rules. Cosine x cosine y minus sine x sine y. And then also with sine x plus y. This is where we ended up last time. It was sine x cosine y, the same sign, cosine x sine y. It's very easy to get it mixed up. The way I remember it is cosine C for constant, so it's cosine, cosine, sine, sine. S for switching for sine, cosine, cosine, sine. These are the angles we did last time. The sum and difference angles. But what if x equals y? What if x equals y? So we have cosine x plus x, which is cosine 2x, the double angle. What's that going to equal? That's going to equal cosine x times cosine x minus sine x sine x, which is cosine squared x minus sine squared x. So cosine double angle, that's one of our formulas. From this one, we can build a couple of more. So here's one of our double angle formulas. From cosine squared x plus sine squared x equals 1, the Pythagorean identity, we get cosine squared x is equal to 1 minus sine squared x. So our cosine double angle is cosine squared x minus sine squared x, where cosine is equal to this. It's 1 minus sine squared x, which becomes 1 minus 2 sine squared x. There's another one of our formulas.
So you're essentially substituting
1 minus sine squared in place of cosine squared. Yeah, that's why remembering this Pythagorean identity, we can now rearrange those. So we have 1 for solving for cosine. We'll do the same thing for solving for sine. And there are packets back there for the rest of the course, next couple of chapters. So that's if we set cosine equal to 1 minus sine. What if we take the cosine squared x plus sine squared x equals 1, and solve for sine squared x. So our double angle which used to be cosine squared x minus sine squared x, is now going to be cosine squared x minus 1 minus cosine squared x. And distribute that, I get -1 plus cosine squared x, so I get 2 cosine squared x minus 1. This is our third equation that we can use. So these are just transformations, just taking what we have already and rearranging it. So those are the ones with cosine. Let's look at the one with sine now. We know that sine x plus x will give us sine of a double angle, which would be sine x cosine x plus cosine x sine x, which would mean 2 sine x cosine x, which is my fourth formula.
Single side.
Right. Yeah, the reason the cosine had it because it was cosine squared minus sine squared, and the sine squareds came perfect from the Pythagorean identity. Sine squared didn't have much to work with. So these are our 4 double angle formulas. Let's see if we have an example. Example 1. If sine x equals 3/5, where x is between pi/2 and pi, find the exact values of sine 2x and cosine 2x. So what do we have to do first?
There's triangle, sine,
Let's find cosine, right? We know sine already. So sine of x is equal to 3/5. So cosine of x will be at least 4/5 because it's a 3, 4, 5 triangle. But it also told us which quadrant are we in. We're in quadrant 2. What is cosine in quadrant 2? Negative. So A. So the sine of 2x will be 2 sine x cosine x. So it's 2 sine x is 3 over 5. Cosine is negative 4 over 5. Four times 3 is 12, 20, and so it's negative 24 over 5. And do the same thing with cosine now. Which formula do you think you'll be using for cosine? Why would we use that? Why? Yes, we already have the sine of double angle of sine. So we use the 1 minus the 1 minus 2 sine squared x. So it's 1 minus 2, 3 over 5 squared. 1 minus 2, 9 over 25. 1 minus 18 over 25. 25 minus 18 over 25 is 17 over 25. Pretty straight, yeah. So it's, you can use any one you want to. Since we also calculated cosine, we could have done cosine also. Since we calculated cosine already. But why would that not be a smart move? What's that? Exactly. Always use what's given to you. Because if sine's given to you, use sine. Don't use what you did. I know you should have more faith in yourself, but use double angles formulas to establish identities. More precisely, we're going to look at developing tangent of 2x. And then we're going to expand it a little bit, and we're going to look at this. What if we have sine of 3x now? So let's first develop tangent. What do we know from tangent x plus y? What's the formula for that one? Tangent x plus tangent y. Then it's 1 over 1 minus tangent x tangent y. When x and y are the same, then we have the double angle. So it's tangent x plus tangent x, 1 minus tangent x, which becomes 2 tangent x over 1 minus tangent squared x. This is our fifth formula that we'll be using. Find an example for that one. No. We have to do the sine 3x first. So how do you think we'll solve sine 3x?
Break it down to cos it, sin x, cos x, plus sin x, plus cos x, plus sin x, plus cos x. Essentially, would be
Well, we'll first split them up, yes, and make it into a sum of two side angles. Because we have both of these defined, we just have to create the formula, which is what's the sine of the sum of the angles? Sine 2x cosine x plus cosine 2x sine of x. Can we go anywhere further from there? Yeah, what is sine double angle? What is cosine double angle? This is going to expand it. So sine double angle, we figured out was 2 sine x cosine x times cosine x. And since we have a sine here, let's do the cosine one with respect to sine. So it's 1 minus 2 sine squared x.
we can use any of them, but we're just choosing.
Choosing because what we have next to them already. So then we have 2 sine x cosine squared x plus sine x minus 2 sine cube x. Was that a good move there? Not really, because we can't combine anything here. Because once we do this, we're stuck. So even though we can work with it, we can't shrink it down any further. So let's try another one instead of this one. So let's try using cosine squared x. The first one, cosine squared x minus sine squared x. Yeah. So that would give us sine 3x is equal to sine 2x plus x, which makes it sine 2x cosine x plus cosine 2x sine x. Now, instead of this one, let's use this. Sine squared x cosine x plus cosine squared x minus sine squared x sine x. Let's see if that helps any. So it's sine x cosine squared x minus sine cube x. Where did I get the square from? That's 2x. Yeah. I was a bit confused here. I got myself confused. It's not sine squared, it's sine 2x. And so what is sine 2x? Sine 2x is 2 sine x cosine x. Times cosine x plus sine x cosine squared x minus sine cube x becomes 2 sine x cosine squared x plus sine x cosine squared x. Now I can combine these two. 3 sine x cosine squared x minus sine cube x. And that's what that equals. Can we do anything else with it? Well, what is cosine squared x? Using cosine squared x equals 1 minus sine squared x. Right now we have a mixture of sine and cosine. Let's say I want only sine to be a factor in there. So that gives us sine 3x, 3 sine x, 1 minus sine squared x minus sine cube x. Three sine x minus 3 sine squared x minus sine cubed x. No, sine cube x. Because that times that. So it gives us 3 sine x minus 4 sine cube x. So now I don't have to worry about converting to sine. our cosine. All right, so let's see what else we have to do. Oh, let's see. How would we address tangent squared x? What is tangent squared x? Sine over cosine. So we want to use these with respect to double angles. So what is sine squared x with respect to double angles?
Yeah.
Okay,
1 minus cosine squared x.
yes, but now where can we go from here? Because remember, we want to try to make it into either one of the trig functions where it's a double angle. That's our goal. We know that cosine 2x is equal to what? We have all those functions for cosine. The second formula was 1 minus 2 sine squared x. So let's solve for sine squared x. What does that give us? So we have cosine 2x minus 1 equals negative 2 sine squared x. Change the signs. So we have 1 minus cosine 2x equals 2 sine squared x divided by 2. So sine squared x is equal to 1 minus cosine 2x over 2. That's our numerator. So now we got to find cosine. What do we know about cosine? Cosine double angle is 1 minus 2 sine squared x. I already did that. So now let's find, we have sine squared, we need cosine squared here. So what are the functions for cosine? 2 cosine squared x minus 1. So cosine 2x is 2 cosine squared x minus 1, I believe, yeah. Let's solve for cosine squared x. Add 1 to both sides. Divided by 2. So cosine squared x is equal to cosine 2x plus 1 over 2. Since sine is one, so we could write it as 1 plus cosine 2x over 2. So the tangent squared x is equal to sine squared x over cosine squared x, which is 1 minus cosine 2x, 1 plus cosine 2x. Take the top fraction, leave it alone. Flip the bottom. The 2's cancel, so it equals 1 minus cosine 2x over 1 plus cosine 2x. So there we have an identity for tangent squared. Let's look for an example here. Example 3. Any questions so far? It's a puzzle. It's consider. Doesn't matter which one. It doesn't matter which one until you get to a point we can't go any further. We can keep on putting identities over identities, but if that one doesn't work, let's try another. Because like in cosine, we have 3 of them to choose from. So it's whatever one gives the most bang for our buck. We use that one. Which one? This one?
1 minus cosine 2
That one?
over 2.
That one.
Yeah.
From right here. That's right. That's the whole thing I worked out here for sine squared. That's what sine squared equals. Okay, this next one says establishing identity, right? Oh, wow, this is cosine to the 4th power. Write an equivalent expression for cosine to the 4th of x that does not involve any powers of sine or cosine greater than 1. So rewrite this cosine to the 4th of x. Write that as a function of sine and cosine where there are no exponents. First step is what? How can we write cosine to the 4th? No. You try that, but no.
Cosine squared x times cosine squared.
Which is cosine squared, right? Because what we have so far, we have cosine squareds. So let's use those and then see where that takes us. So what is cosine squared x? We just worked that out. Yeah, 1 plus cosine 2x. So this is 1 plus cosine 2x over 2 squared. We just worked that out here for cosine. One plus cosine 2x squared over 2 squared. So this becomes 1 plus cosine 2x, 1 plus cosine 2x, which becomes 1 plus 2 cosine 2x plus cosine squared 2x. I just FOILed it. That's what this says. And foiling it gives me this. Okay, let's see what this gives us. So we have 1/4 plus cosine 2x over 2 plus cosine squared 2x over 4. So these are good so far. They have no exponents in those. This is the only one we have to worry about. So what's cosine squared? We know cosine squared x is this. So what if our angle was 2x? So it'll be 2 times 2x here. So that would be 1/4 cosine 2x plus, that one's going to be 1 plus cosine 2 times 2x over 2. Because we have cosine squared x is equal to 1 plus cosine 2x over 2. Since we have a 2 in front of there, we have to multiply that by 2. So what happens here? And then what we do here, yeah, because now we have constants here. We have 1/4 plus cosine 2x over 2 plus 1/8 plus cosine 4x over 8. Then we combine these two, which makes it 2/8, which makes our final answer what was our original? Cosine 4x is equal to 3/8 plus cosine 2x over 4 plus over 2. That's over 2. Plus cosine 4x over 8. The difficulty level of this one would include what? First off, knowing where to start. Going from here to here. Why is that the only logical thing we can do? Yeah, because we have formulas with cosine squared x. Once we do that, then we could just expand it. And then from there, that gets rid of all of our exponents. Example 4. Yes. For this, you could actually, yeah, you could. That wouldn't be dumb at all. If you want it to look nice, that's really, that actually, you're right, that looks much cleaner because it's over one fraction only.
That would be the most likely input for the.
Solution for the computer, yeah. Because it's space expensive entering it this way for the computer. Because it has to analyze each keystroke, as opposed to this. It just looks at the numerator, it looks at the denominator, and you're done. Yeah, this is what the common convention of mathematics says you're supposed to do. Example 4. Solve trig equations using identities. Solve sine x cosine x equals -1/2 for our x being in this domain from 0 to pi. It means everywhere. So do we have any identities we can use here so far? Let's look at our formulas.
Half of sine 2x.
Right, sine of 2x would equal what? We know sine of 2x is equal to
Sine x.
our 2 sine x cosine x, right? Or is that sine squared? Sine 2x is equal to that, right? You're right. This is half. Well, there's that 2 there. What if I multiply both sides by 2? Then I get 2 sine x cosine x equals -1. As long as you do the same thing to both sides, you're good to go. So what is sine 2x? 2 sine x cosine x. That's sine 2x equals -1. Where do we get to the half angles? Oh, there we go. So what do we know so far? What do we have to find? We're looking for we're solving for x. What does x have to be to satisfy this condition? Where is sine equal to -1? Yeah, at 3 pi over 2. So we know that our equation has to be some form of 3 pi over 2. So our sine x, our sine of 2x, x has to be that. So we're looking at 3 pi over 2 plus, does it repeat itself cyclically? So 2 pi k times for every 2 pi. So when k is 1, that's 1 circle. K is 2, K is 3. So this is the formula we'll be using. So that has to equal -1. So what we have here is our 2x has to equal 3 pi over 2 plus 2 pi k. Solve for x, what do we get? Because we're looking for the angle. Divide by 2, everybody. We get x equals 3 pi over 4 plus k pi. Why is it this? Because remember, it's a double angle. This is for sine 2x. So when we look at when k equals -1, when k equals 0, when k equals 1, when k equals 2, we just calculate those and see what we get till we start repeating itself. So 3 pi over 4 minus pi, which is 4 pi over 4, which is negative pi over 4. When x is 0, it's going to be 3 pi over 4. When x is 1, we have 3 pi over 4 plus 4 pi over 4, makes it 7 pi over 4. And when x is 2, we have 3 pi over 4 plus 2 pi, makes it 8 pi over 4, which makes it 11 pi over 4. So what's that?
And this is what we need to know our periodicity.
Yeah, so which ones can we use? Because we have to be within our domain of 0 and 2 pi. So which ones satisfy the condition? Because when k is 0 and when k is 1, this makes it too far. Because this goes over 2 pi. So we can't use this one. We can't use this one. So, well, we could use that. It's going to give us, we have to convert this now to positive side. But so our two angles we'll be using are 3 pi over 4 and 7 pi over 4. That's what that one says. So again, how do we do it? We first have to get it to a point where we can compare the two. What is the period for this function? It's 3 pi over 2, because it has to equal -1, and it's every 2 pi k. So then we take this has to equal that, and we solve for it. It's a adaptive construction. We're building up on it with what we know from the previous step. Projectiles. This is how what Newton was working on when he really developed some of the concepts he did for his mathematical research from Principia Mathematica. He was looking at the British military practicing their cannon fire, and he noticed one thing. He said that you have two chances of shooting your enemy, depending on how you want to do it. If your cannon is here, there's only one angle that gives you the maximum trajectory. Anything else after that, you can either go high or you can go low. The low one will bounce afterwards. The high one will make a more explosive impact. And so it said, depending on what kind of army is attacking you, it may be better to have a lower angle and let the ball just keep on flying through there and just tearing up people, as opposed to once it hits the ground, it explodes and that's it. It's no longer useful. So this is stuff he was researching and working on when he was watching all this stuff. All right, this one says an object propel upwards at an angle X. Object propelled upwards. Angle X to the horizon. With initial velocity v sub 0 feet per second. If air resistance is ignored, the range R which is the horizontal distance, is given by this function. R of X is equal to 1 over 16, the initial velocity squared, sine X, cosine X. And that's defining this trajectory, where this is the angle X. First question. Show R of X equals 1 over 32 VO squared sine 2x. B, find X where R of X is a maximum. So what's our first step we have to do? What are we looking for in the first step? We have this formula here. Right, notice this is a doubling. So how do we convert it? This one. So 1, we have R of X is equal to, no, this actually equals 1 over 16. We're trying to get 1 over 32. This kind of looks similar to one we just had. Sine X, cosine X. Looks similar to what? It's a double angle. It's a double angle of sine, remember? Sine 2x is sine x cosine x, or 2 sine x cosine x. So this would be sine x, or 2 sine x cosine x over 2. We're just multiplying by 1. We're not changing anything. This 2 comes out in front. What is 2 sine x cosine x? This is sine 2x. That's the identity, which is what we're trying to find.
Where the 1/2 come from?
Because we had sine x cosine x. The formula for sine square double angle is 2 sine x cosine x. So we have to put a 2 there. If you put a 2 here, we have to put a 1/2 to get rid of that 2. So basically what we're doing is multiplying by 2/2. This kind of stuff here, that causes the most problems is when do you just multiply 2/2? When can you, when can you not? Whenever you multiply by 1, you're not changing anything. But if you do it, you have to do it universally and uniformly. So that's the first one. We proved that the double angle is 1/32 initial velocity squared. Find x, the angle where the distance is maximum. This is B. Find x where R of x is a maximum.
This would be a upside or a parabola opening downwards.
Right. It's negative parabola. This opening downwards. So how do we do this? What do we have to do? We know the initial speed is fixed. You can't change that. So let's put the formula down again. What is that formula? 1/16. What do we exactly do we have to find? To make this, because if we make cosine 1, what happens to sine? Where is cosine 1? 0 at horizontal. Where's sine 1? Where it's vertical. So how do we fix this? Where do we think the most optimal angle is going to be? Well, as we just looked at, we can convert this to 1/32 VO squared. So all we have to do is worry about, instead of working sine and cosine, if we do double angle, right. And sine deals with which axis? The y-axis. So the maximum sine can have is what? The maximum sine can have is 1. Where does sine get the angle of 1, or the value of 1? When x is 90 degrees. So it achieves its maximum value at 90 degrees. So if we take 2x and set that equal to 90 degrees, where sine gets its maximum value, then x is equal to 45 degrees. That will give the function its maximum distance. Because remember, think about it. Sine and cosine has to be between 1 and -1. For maximum, we can't have negatives. So we have to go from 0, and we can't have a 0. So the maximum we can go to is what's the highest value we can get is 1. How do we get to 1? For the double angle, the only way that happens is if 2x equals 90 degrees, which makes it x equals 45 degrees. That's the angle. That's the answer we're looking for. Some of these are very intuitive. Some of them we have to think about it. And And because that's what, and here's another thing it tells us. There's a reason why, there it is. Right here. The first part, we found this. We didn't have to worry about sine, cosine anymore. We got this. So let's use this formula. The maximum value this can get is if when this is +1. Anything smaller, decimal wise, you divide by 32, it gets much smaller. So no. Use half angle. Formulas to find exact values. Let me see. I have to see what time I have to be at my cardiologist. Well, you know. How do we define our half angle formulas? Okay. Yes, this is, but what would that equal? How do we derive it? For us to save time, I'll just give it to you. Tangent. So these are the formulas we have for our half angles. So we go from there. What is the half angle of sine? What's the half angle of sine? Missing something. Nope. You're close. You're halfway there. Plus or minus. Because whenever you take the square root of a squared term, you have to put a plus or minus in there. So that then cosine function would be plus or minus 1 plus cosine. And then tangent x over 2 would equal plus or minus 1 minus cosine x over 1 plus cosine x. Let's do an example. Let's see how we put the stuff into action. Find the exact values using half angles. Cosine of 15 degrees and sine of negative 15 degrees. So how would we write cosine 15 degrees as a half angle? 30 over 2. So that equals, so cosine is equal to plus or minus 1 plus cosine of 30 over 2. And then the sine would be negative 30 over 2, which would be plus or minus square root of 1 minus cosine of 30 over 2. But since sine at negative 15 degrees is negative, this one has to be negative. Cosine at 15 degrees, what's the value of cosine in the first quadrant? So it has to be positive. All right, so now let's work inside there. What is cosine of 30 degrees? Square root of 3 over 2. Now, how do we fix this? So I need more space. So this is going to be 2 plus radical 3 over 2 over 2. It's a fraction over a fraction, complex fraction. So take the top fraction, flip the bottom. So we have 2 plus or minus which becomes and there's your answer.
Or essentially it's in square root 2 plus square root 3 over square root 4, which simplifies to
2, right? Yeah, I just went ahead and split these up. This is part and part bottom. And likewise, now we have the negative side. So cosine of 30 is square root of 3 over 2 over 2 negative there's going to be 2 minus, so it's 2 minus square root of 3 over 4, which becomes negative square root of 2 minus square root of 3 over 2. Pretty straightforward. Next example. We're going to now find exact values using half angle formulas. Find exact values using half angles. If cosine of alpha equals negative 3/5 and alpha is between pi and 3 pi over 2, so it puts us in which quadrant? Third quadrant. Find the exact value Find the exact value of a sine alpha over 2 cosine alpha over 2 and tangent alpha over 2. One thing you have to be careful about is, remember, we're looking at this domain. We want alpha over 2, right? So we have to divide each of these by 2. So this falls in which domain? And now we're in region 2, quadrant 2. Because pi over 2 is straight up, 3 pi over 4 is 45 degree angle in the second quadrant. So when we switched from angle alpha to half angle alpha over 2, we've switched quadrants. What does that do? It changes the sign of your answer. So A, sine alpha over 2. Since we're in quadrant 2, what's the sign of alpha over sine in quadrant 2? It's positive, so we just use the square root of 1 minus cosine alpha over 2, which is equal to 1 cosine. We figured out, we were told, is negative 3 over 5. Cosine alpha is 3 over 5, negative 3 over 5. One plus 3 over 5. So it's 5 over 5 plus 3 over 5. 8 over 5 over 2 over 1. We have 8 over 5 times 1 over 2. That equals 4. So we have square root of 4 over square root of 5. Rationalize the denominator. So we get 2 radical 5 over 5. You're staring at it like it's got 3 eyes.
No, was that? I guess I figured we were simply given cost, we would figure out time first, but since it.
And that's the beauty of it. All these formulas will have cosine as the function. On your homework or tests, it'll give you sine, but on the examples, it'll give you cosine. So yeah, but normally, if they gave you sine, then you find cos. But since they gave us cos, all our formulas with cos, we just plug and play. But the only thing you have to worry about is what sign you're using. So for the sine angle over 2, we're in quadrant 2, it's positive. There you have it. The cosine of alpha over 2 is 1 plus cosine of alpha. And in cosine, in quadrant 2, we're negative. So we have 1 plus negative 3 over 5 over 2. Negative 1 minus 3 over 5 over 2. Common denominator. So it's 2 over 5, 2 over 1. These cancel. So we have square root of 1 over 5, which becomes 1 over square root of 5. So it equals negative radical 5 over 5. Negative. Make sense? You're looking at it.
I'm looking into,
You got it?
Mhm.
Okay. That's,
Cause I did not get a picture at all. I just remember formulas from geometry and algebra. That was it.
the hardest part of calculus when you see it is going to be basic algebra. It's because you're thinking it can't be this simple. It's got to be more, it's calculus, it's college calculus. It's got to be more difficult than that. Now we got to do the tangent. So the tangent of alpha over 2. In the second quadrant, it's what? It's negative. So it's 1 minus cosine alpha over 1 plus cosine alpha. One minus negative 3 over 5. 1 plus negative 3 over 5. Negative, this makes it 5 over 5 plus 3 over 5. 5 over 5 minus 3 over 5. Eight over 5 over 2 over 5. So that cancels there, that cancels there. This is 4 now. So negative square root of 4 makes it negative 2. Is there an easier way we could have done that tangent one? Well, we found out, we know what sine is. Sine was 2 radical 5 over 5. Cosine was negative radical 5 over 5. Take the top one, leave it alone. Multiply by the flip of the bottom. Fives cancel, radical fives cancel, so we're left with -2. That would be faster. Well, that's it for that section. Yeah, it's very long because it builds on so many other things. The derivation of just the first from sine and cosine, who ever thought that cosine would have 3 derivations of different formulas? And then we use those to go even further, even more derivations of them. So that's it. Let me, let's see where that puts us.